Hello, everyone. I'm Louis Wang. It's my pleasure to share our recent work, Rethinking the Embodied Gap in Vision and Language Navigation, a holistic study of physical and visual disparities. Here is the agenda for today's presentation. We start with a brief introduction to VLN. Vision and Language Navigation, VLN, is a cross-domain technology. It places an agent in a real-world visual environment and requires it to navigate to a specified location based on natural language instructions. VLN maps perception data to action decisions, bridging robotics, computer vision, and natural language processing. As robotic applications expand, traditional navigation faces many uncertainties. Navigation goals vary due to differences in instruction format, target type, and user habits. Operational environments are uncertain due to domain shifts, unknown spaces, and dynamic scenes. VLN provides an effective way to handle these challenges. Next, we introduce the VLN-PE platform proposed in this work. Let's first review the two commonly used VLN simulators. Matterport 3D Simulator 2018 predefined discrete topology points and idealized teleportation using real indoor photos. It laid the foundation for early research but limits movement flexibility. Habitat 2019 continuous 3D space with continuous control actions in reconstructed scanned scenes, improving environment realism and model generalization. ICCV NVIDIA 2018 supports multiple scenarios and robot types, integrating manipulation and navigation. Intern Utopia 2024 features realistic physics and rendering, supports various robots and RL training deployment, providing strong support for VLN simulation platform development. In summary, MP3D's idealized teleportation limits system robustness. Habitat's virtual robot slides without physical simulation, reducing model generalization. Intern Utopia, powered by a realistic physics engine, supports multiple robot types and diverse scenarios, demonstrating strong scalability. To systematically study the embodied gap in VLN and investigate physical-visual discrepancies, we propose VLN-PE, offering both theoretical support and a research perspective. VLN-PE is the first physics-based VLN simulation platform developed on NVIDIA Isaac Sim and Intern Utopia. It supports humanoid, quadruped, and wheeled robots and can operate in scanned scenes, modeled scenes, and Gaussian splatting rendered environments, enabling training and evaluation across varied scenarios. The simulator can also load high-quality, realistic modeled scenes. Limited by current robots equipped with a single RGB-D camera, we systematically evaluated several common VLN-CE baselines under this setup. Sequence-to-sequence baseline, a simple Jew-based decision model. CMA builds on sequence-to-sequence with an attention module to improve cross-modal fusion. NVID, a practical vision language action, VLA, model generating executable actions with quantitative parameters. Inputs are language instructions and navigation video segments. Outputs are discrete actions with specific values. It is the first VLA large model effectively applied to VLN-CE. All three are classification models, outputting 4 fixed actions: forward, left, right, and stop. Inspired by diffusion policy algorithms, we also propose the first diffusion-based recurrent network, recurrent diffusion policy for VLN, RDP. RDP, the first diffusion policy approach for VLN. Inputs include RGB and depth observations, language instructions, relative start coordinates, and previous relative actions. Outputs are continuous offset coordinates for the next 8 steps. We also validated a training-free map-based LLM method. Classic VL maps cannot be directly applied to VLN, so we introduce a frontier-based exploration approach to enable zero-shot application. During algorithm evaluation and discussion, several key questions arise. Discussion 1. Models trained on VLN-CE show significant performance drops when transferred to VLN-PE. For example, the 3 classic classification models show an average success rate drop of 15% when directly transferred. Training small models on a small amount of VLN-PE data can even outperform classic models trained with large-scale data augmentation. Discussion 2. Model performance is sensitive to different robot platforms. It is affected by viewpoint, height variation, jitter, falls, and deadlocks, highlighting the importance of platform adaptation for optimization. Models are especially sensitive to motion dynamics and camera height. Data from a specific robot improves adaptability, while cross-robot data enhances overall performance, demonstrating one-for-all potential. Model performance is closely related to the type of physical controller used during training and evaluation. Matching controller types improves performance, emphasizing the importance of controller consistency. Models trained on standard MP3D datasets generalize poorly to out-of-domain scenes. To address this, we introduced two new datasets, GRU VLN-10, high-quality modeled scenes 3DGS Lab VLN, Gaussian splatting rendered scenes, improving generalization. Focusing on lighting sensitivity, we find that pure RGB models are more affected by varying illumination. Finally, evaluating CMA models on Unitree Go 2 shows that training on VLN-PE significantly improves real-world deployment performance. Thank you for your attention. Here are QR codes to the paper and code for more details.